V and W with finite dimensional vector space. V and W, these two are finite dimensional vector space. In short, I can write finite FD Vs, finite dimensional vector space, and T is a linear transformation from V to W. We have four options. Dimension of V less than dimension of W implies T cannot be onto. Option A, dimension of V less than dimension of W implies T cannot be onto if I make a matrix representation of this linear transformation, then the size of this matrix would be dimension of W by dimension of V. It means W comes here, dimension of W becomes row, number of rows, and dimension of V becomes number of columns. If dimension of V is less than dimension of W, it means number of pivot elements, number of pivot elements is greater than number of pivot elements in column, which is not possible if number of pivot element in a row greater than number of pivot element in a column, because of if there are 3 pivot element in row, it means 3 pivot columns becomes. So this is not possible. So T cannot be onto. For this, first you can recall, if we are saying onto or 1 1, for onto we see pre-image in domain. So dimension of domain should not greater dimension of pre-image should not less than dimension of domain points. It means dimension of pre-image subspace. I will call subspace, dimension of subspace of pre-image should not less than dimension of codomain elements for onto. But for this dimension of V is less than dimension of W. So option A is correct. T cannot be onto. And same reasoning for option B. If dimension of V is greater than dimension of W, T cannot be 1 1. For this, if we see, these two are subspaces. I will call one as a domain and second one as a codomain. We are seeing 1 1. It means image is going here. So dimension of this, it means the dimension of codomain should not less than dimension of domain. And in this dimension of W is strictly less than dimension of V. So this option is also true, because T cannot be, this word please keep in mind, cannot be. Dimension of V plus nullity of T equals to rank of T. This is wrong, because of V well known rank nullity theorem, or this law is known as Sylvester law. Dimension of V equals to dimension of W. This implies T is invertible. In this case, if dimension of two subspace means domain and codomain if same, then T becomes invertible. T becomes invertible or not invertible, means not 1 1 and not onto, both. If become 1 1 and onto, if not, then not 1 1 not onto. Both cases are possible. So this option D is also wrong. So correct option for this problem is option A and D.